Hello and welcome to another video on Introduction to Statistics, where we're going to do a little example demonstrating the t-test for a single sample. The book that we're going to get this question from is my favorite, Statistics for Psychology. Even if you're not interested in psychology, the statistical principles and concepts are the same and extremely well explained. We're going to go to page 267 and look at number 15 over here. So let's read it first and see where we are at. In a particular country, it is known that college seniors report falling in love an average of 2.2 times during their college years. A sample of 5 seniors, originally from that country, but to have spent their entire college career in the United States, were asked how many times they had fallen in love during their college years. Their numbers were 2, 3, 5, 5, and 2. Using the 0.05 significance level, do students like these, who go to college in the United States, fall in love more often than those from their country who go to college in their own country? Use the steps of hypothesis testing, and I'm going to leave the other questions for you. Just the basics today.
Welcome to MathCats, where we aim to better understand mathematics. Join us weekly for discussions on elementary, high school, through to university math. You can request the next topic by leaving a comment on our YouTube channel or by emailing us at mathcats314@gmail.com. And as always, remember to like and subscribe. Thank you.
I see my camera is not really working. I apologize, but we'll continue. So let's think about this. I have two populations. I have people that from this country, college seniors rather, that go to college in the US versus college students from this country, college seniors, that do not go to college in the US. And we're trying to see if they stay in their country, the average, the mean distribution of this property that they're measuring is 2.2, the mean of the distribution. And we want to see, is it more? Where's the question here? Do students like these who go to college in the US fall in love more often than this 2.2 based on this sample? So I'm going to use Excel just as a glorified calculator for the huge convenience, but you can totally do this by hand as well. So let's just put in these numbers here. What is it? 2, 3, 5, 5, and 2. Let's put in 2, 3, 5, 5, and 2. The mean under the null hypothesis is, let's maybe write that in here somewhere. H0 is that the mean is 2.20. And the alternative or research hypothesis is that the mean is greater than 2.20. My sample is, of course, here 5. And as usual, I use yellow cells to indicate sort of input given numbers, like alpha is 5%, and green will be where we do calculations. But the benefit of this is that we don't lose any of the calculations and we don't have to write them down. So first of all, I need to calculate the mean of the sample. So here are some functions that might be handy to remember, but the beauty of Excel is that you don't really have to remember it. You could just search for mean and in this case it's called average. And you can check the description there. The arithmetic mean is exactly what we're looking for. And then I can just highlight and say everything in that range, please. And I click on OK, and boom, there's the average. And we'll call it M. Then I need to get an approximation for the variance. That's going to be my S squared. Remember the degrees of freedom. We'll do a calculation. Is 1 less for my t-distribution, 1 less than the sample size. I could have just put in 4, I know, but I want to get used to this calculation in Excel. So there are a few steps here for calculating the variance of this sample. First of all, the square of the difference between the raw score and the sample mean. So we can, I have to tell Excel with an equal sign, I'm going to do a calculation, or a function is what it calls it, the raw score. Take away the mean difference, and then I'm going to square that. And you see here it used this cell and that cell. Now I want this red cell to always be used as I copy this formula down. So I'm going to put my cursor inside, press F4, and it's going to fix the location of that cell. And then when I go to this bottom right corner and drag it down, I can double check another calculation. You see the blue one moves with me, it's all relative, but the red one stays as it should. Check over here, blue one moves with me, uses the appropriate raw score, but the red one is always the mean. Okay. Then we're simply going to do the sum of the squares, sum of the square differences here. So for that, we're going to look for a function, and it's going to be called the sum function. I happen to see it there, right there, adds all the numbers. That's exactly what we're looking for. And again, remember, if we're going too fast, you can always scroll back, watch something again. You can slow it down, half speed, whatever you need. So we're going to add up all of these and get 9.2. And then the variance is the sum of the squares divided by n-1, or the degrees of freedom. Let's calculate that. Sum of the squares divided by degrees of freedom, and I get 2.3. Now, in my hypothesis test, the comparison distribution, remember for a sample, is the distribution of means. We'll call that SM. Now I can do the variance of that distribution first and then take the square root. You decide. Maybe we can do that. Let's move all this down one. Just going to shift this down a little bit. And maybe I want S but squared. So the variance of the distribution of means. That is going to be the, clear my throat a little bit, the variance of the distribution of the individuals in the population divided by the degrees of freedom. Well, no, not the degrees of freedom. N. Get rid of that. Sample size. Sample size N. 5 in my sample. Enter. So I have the variance over N. Another way, of course, depending on how you remember it, you could look up these formulas. Now, I don't know exactly all these formulas are necessarily in the front of the book. A lot of them are, not necessarily all of them. We had the variance, sum of the squares divided by degrees of freedom, n-1, formula 7.1 or 7-1. Then here we have the variance of the distribution of means that we just did, the population variance divided by the sample size, that's what we just did. And then in my t-distribution, I'm going to use the standard deviation instead of the variance. So I need to square root that answer for future use. So we just did individual variance or population variance divided by n. We just did that, got 0.46. Now we just have to take the square root of that. And sometimes you remember SQRT. You see, it's sort of guesses. Well, these are your options. Yep, I want that one. Nope, I apparently did not do that right. Tab will sort of auto-complete it and capitalize it. I want the square root of this number, please. Close my bracket, enter, and there we go. Now all I have to do is, perhaps we want to visualize this. I just have an old example here, but we can totally make a new one. I'm doing these videos back to back, but there's a new page. We can visualize what's happening here. Let's go full screen. And let's zoom in a little bit. That's too much zooming. There we go. So if I'm visualizing this t-distribution, which I'll draw the same as the bell curve, its tails are a little bigger. Symmetry is my drawing problem. That's not great, right? We can do that again. That's good enough. So I'm positioned here at 0, sort of this t-distribution, sort of the version of the standard normal distribution when I have to approximate the variance. So now in our case, we wanted to see if it was more specifically after this, I guess, treatment, quote unquote, of going to college in the US. So we had alpha of 5%. So it's one-tailed on the right. So I need to know what is my t cutoff score. So that we can look up in a table, or we can use Excel. It has all these tables already in there. Actually, it has the function. So it can be very accurate. So I don't have to memorize these. I just put it on the side there. Let's suppose I have no idea, right? I don't remember. I know it's a t-distribution. I'll search for t-distribution. Search or go. And yes, there's a bunch of other things here. I'll look through my list, look for t-distribution. They're alphabetized, so I want to go down to t-distribution. Now there's a couple of them. I have the left-tailed, two-tailed, and right-tailed. Now, it doesn't really matter. If you want to be consistent, you can just use that one and make your own adjustments for the alpha and realize this is always sweeping it from the left. And so that's fine. You don't have to mix things up too much. However, the t-distribution function is going to take a raw score, of course, the degrees of freedom, and give you the probability. That's not what we want, right? Alpha is our probability on the right. Let's have a look at this again. If 5% is on the right, then all of this is going to be 95% on the left. So we want the inverse of the t-distribution in terms of what it gives me. I have the probability. I want the t-score. So that's the one I'm going to use. What's the probability? Well, it's the left side, right? And I happen to have a one-tailed test on the right, so I have to say 1 minus alpha. And my degrees of freedom I found up here is 4. And there we go. So our cutoff t-score is 2.13185. Let's put that in here. What did I just say? 2.13. 2.13. Cutoff t-score. Now I need to calculate my observed t-score and compare them to see what my decision is in my hypothesis test. There's some handy formulas here. Sample mean, minus the mean under the assumption of the null hypothesis over the standard deviation of the distribution of the comparison distribution, which in this case is the distribution of means. So let's put that calculation in, or let's do that calculation. I'll open some brackets. Sample mean minus null hypothesis distribution mean over standard deviation or approximation of the standard deviation for the comparison distribution, which is the distribution of means Sm. And I get 1.77-ish. 1.77. Let's visualize that. It's very handy to visualize that. 1.77. Ooh, that's over here. So my T observed, 1.77, is not past the cutoff. It's to the left. So we take that as not strong enough evidence to suggest that the null hypothesis is not true, because it's very likely to get something in this area, which is why we have that cutoff line to base our decision on. So we can say, let's say conclusion here, since the T observed, just one S, is less than the T cutoff, we do not have strong enough evidence to reject the null hypothesis. Just in case you weren't clear, do not reject the null hypothesis. The evidence is not strong enough. So there we go. Very straightforward and a good sort of template example for how we can do hypothesis testing with our T distribution and one sample. Using Excel just to make the calculations a little bit more convenient, but they're all the same as if you were to do them by hand. Feel free to leave a comment, questions, everything is welcome. Until next time then. Thank you.